All right, so we are going to be explaining the flame test today, as well as the spectroscopy activity we did earlier in this unit. What we have on the screen right now is a simulation of our flame test. On the left, we have a model of the atom known as the Bohr model, B-O-H-R. On the right, we have a metal bar where our substance is and the flame. And on the top, we have our emission spectrum. This is the emission spectrum for strontium. And I know that because if you look at the bottom of the screen, we see that strontium nitrate is selected. All right, so again, right, this is our setup. We have our atom on the left. We have our tool on the right that we can move into the flame. This is mimicking our Q-tip with the substance on it, and our emission spectrum at the top. Now, we are going to look at a few different samples today and explain what's happening. Right, so we have this strontium nitrate selected right now. And what we'll do is, in just a second, we're going to move that strontium nitrate into the flame. Now, we see that the strontium nitrate immediately turns the flame red. Maybe you also notice that on the left, we have these lines popping out of the atom, and we see that there sometimes are more circles and then less circles again, as these wavelengths, these waves of different colors are coming out of the atom. Now, these waves of different colors coming out of the atom are representing the different wavelengths of light that the atom is emitting. So these are those reds and those greens and those blues and those purples that create this red color that we see. Now, why is that happening? Well, you'll notice that every time a wave of light of different colors is pushed out of the atom, it comes out of the atom, something is happening with the electrons. Those dots circling that center part, which is the nucleus, those dots represent electrons. And we see that every time they jump around that and then jump back to their original position is when the light is emitted. This is because that's exactly what is happening, right? When the atom is exposed to this heat source, it is absorbing light, is more absorbing energy, right? And that's allowing these electrons to move higher up to a higher energy level. When they fall back down again, because that top area is not very stable, when they fall back down again, they have to release the energy they absorbed. And they release that energy in the form of light. Now, we're now looking at sodium chloride. This is another substance we used in our lab. And we see that it has a much smaller spectrum, emission spectrum, than strontium did. It really only has that bright yellow and that very light green. It's also a much smaller atom than strontium. It has fewer electrons and fewer electron levels. So we see when we put this into the flame that it is a yellow color, and we see that only a few different wavelengths of light are being emitted by our atom. Now, this is because this one electron on the outermost level is only making very small jumps. It is going from 3s to 3p. So these are both the S and the P, these are subcategories of our third energy level, and we're going to talk about those soon. They're called orbitals, and they're making just these very small jumps. Right, and those very small jumps mean that only a very little bit of energy is being absorbed, therefore only a little bit of energy is being released. And this is why we're seeing more of a red color, red or yellow color. So in this one, we have the copper chloride, and we see it's green. Now, it is also making those little small jumps that we saw before, but now, instead of it being a yellow light, it is a green light because those jumps at a higher level actually represent more energy. This is, of course, the potassium that was not purple in our experiment. This is the color it should have been if it was a pure enough sample. And we see the same thing is happening. It is jumping all over the place, but it is making some really large jumps from level 3 all the way up to level 5. And this jump takes a lot more energy. And so when it's released, it's really being released as a much higher energy light. Purple is our highest energy light. So when those big jumps are happening and that electron falls back down again, it has to release a very high energy light. Now, let's go ahead and talk a little bit more about what's going on here, right? So we're seeing these jumps happening again and again, and we are seeing very specific colors of light come out. Now, the color of light that is emitted is determined by the size of that jump. And this actually tells us a lot about the structure of the atom. So we're going to go ahead on page 8 and take a few notes. Basically, what we're going to do is we're going to summarize what we just discussed just on paper so you can reference it. Okay, so what is actually happening in this lab? Why is this evidence of electron and their arrangement? And how does this help us better understand the structure of the atom? So what we have here is we have a diagram of the atom with some labels. And so what actually is happening in this lab is when the atom is exposed to an energy source, right? We're really talking about heat or electricity. Its electrons can absorb that energy and move to a higher level. That's what it's doing, right? It's taking in that energy, and those electrons are jumping up to a higher level. Now, right, I say heat or electricity, right, because this is the same thing that was happening in the spectroscopy activity, right? We saw these gases in these tubes, in these glass tubes, and we had an electrical current running through them, and those little gas atoms, those electrons in those atoms were getting that energy, taking that electricity in, and then moving to a higher energy level and then falling back down again and releasing the energy as light. Now, again, right, we're releasing it as very specific wavelengths of light. And I'm saying wavelengths because, well, it's another way of saying like a specific shade of light. Right, so when the atom is exposed to energy source, its electrons can absorb that energy and move to a higher energy level. And we should all be writing this down in our packets. Now, when the electrons return to their original energy level, right? Because they have to. They can't stay up there, right? It's not really stable for them to stay up there. So when they return to the their original level, they have to release all of the energy they absorbed. And they release that energy in the form of light. So everyone should be writing this down in their packets. When the electrons return to their original energy level, they release the absorbed energy in the form of light. Right, so the specific color of light that they absorb, or they release, depends, of course, on how much energy it took for them to make the jump. So that is also something that is important to remember. Now, in just a second, we are going to do this. We're going to color code this diagram on the left as well. But right, we want to make sure that we remember that the color is determined based on the size of the jump, right? So this also tells us that there are specific levels within the atom, right? Like if there were no levels in the atom and it was just electrons were everywhere in the electron cloud, and they were just moving wherever they wanted to. And if they absorbed and then released energy, they could make any jump they wanted. But instead, we are seeing very specific colors of light coming out of very specific atoms, which tells us that it takes a certain amount of energy for the electron to change positions, which also suggests that there are specific levels within the atom that the electron can move to, right? So this tells us about the organizational structure of the atom and where the electrons are in the structure. So let's go ahead and add to our papers right now a few more notes. So we're going to add in now this. And that is that the size of the jump made by the electrons and that it determines the color of light released. Right, the color of light released by the atoms. Oh, sorry, by the electrons. Right, it's the electrons releasing that light. All right. So next, we're going to go ahead and fill in this diagram that's on the left so that it makes a little bit more sense. So on the left here, we have an atom, and its electron can jump to a few different places. It could jump from level 1 to level 2, and back. It could do level 1, level 3, and back, level 1 to level 4, level 1 to level 5, right? And each jump that it makes, it requires a different amount of energy to make that jump, and therefore it releases a different amount of energy when it falls back down to its original position. So the color of light depends on how much energy had to be absorbed. So in this first jump, right, this is a 656 nanometer wavelength of light, and that's an orange color. So making that first little jump, right, it's not going to take as much energy, so we're going to end up with like more of the warmer colors, so yellows and oranges and reds to make that small jump. Next, we have a larger jump, and so this is level 1 to level 2. This is a 486 nanometer light, and this is going to fall in the green range. Remember, we're using nanometers as the wavelength, the length of the wave of the light, because it's a little bit more specific than saying green, red, yellow, right? It's a little bit more specific. So next we have the blue. So this larger jump is going to be the blue. So that's 434 nanometers is in the blue range. And lastly, we have a purple. So that's the 410 nanometer range. So we can see how that much larger jump takes a lot more energy to happen. It takes more energy to make the jump, and therefore it releases a higher energy light as it falls back down than in the oranges, where that's a much lower energy light, and so it takes less energy to make that jump, right? That's what it tells us, is that there's some smaller levels within the atom as well as some larger levels. So we're going to summarize this by answering this question at the bottom of the page. How did this lab better help us understand the structure of the atom? Right? So this lab actually helps us know a lot about the structure of the atom, right? It tells us that there are energy levels in the atom. We didn't necessarily know that before, that the electrons are in specific levels. We know that because the atom releases distinct colors of light, right? It just doesn't release everything, right? All right, so let's write this down. We learned that the light emitted from the metal cation was because of its electrons moving up to a higher energy level and back down again, right? So this told us that there are energy levels in the atom, right? So that is an important thing to know. And that's going to be a foundation for everything else we're doing this unit. This understanding that there are specific energy levels in the atom, and also the way that electrons fill in those energy levels. This tells us not only about the behavior of the atom, but also what its properties are, how it interacts with other atoms, and more. These energy levels are very important. All right, so we're going to take a few minutes and finish up with these notes. Make sure you have everything written down, and then we are going to turn to our last bit of today, which is looking at some definitions on page 1, and then going over how to draw Bohr models. So I'll just go ahead and move this so you can see it a little bit better, hopefully. And there we go. And awesome. So I'm going to leave this up for a minute so that you can finish writing down your notes. All right, everyone. So we are now going to continue with some vocabulary today. So our vocabulary terms that we're going to go over today are electron, emission spectrum, energy level / electron shell. These two words are interchangeable. Excited state and ground state. Now, it seems like a lot of vocab, but it really isn't going to take very long because some of it we already know. So we actually already know what an electron is. An electron is a negatively charged subatomic particle found outside the nucleus of the atom. Now, I want you to remember something, right? This word subatomic. Remember that the prefix sub means below or smaller than, like submarine is a ship that goes below the water. A subway, right? Not the sandwich. But like in New York, that's what we call the underground train. It's a way to move underneath the ground. So this is below an atomic. We are talking about the atom, right? Below atom size is what this means. So that is what an electron is. This is very important to this unit. Next, we have emission spectrum. Emission spectrum. Now, we've been talking about this so far, and I wanted to give us a quick definition of emission spectrum. So this is the specific wavelengths of light. Remember, we can also think about wavelengths as colors, just even more specific than just saying yellow. It's like a very specific shade of yellow that's, I guess, given out by a specific wavelength. So the specific wavelengths of light that are emitted by an element when it's exposed to an energy source. All right. So next we have energy level / electron shell. Let's get this focused again. Now, we have now talked about this a little bit, but we're going to give ourselves a definition. So an energy level is an area in the electron cloud. Right? So remember, the electron cloud we now know is divided up into levels, right? We call these energy levels. It's an area in the electron cloud that contains electrons with the same energy. Right? So these are contains the same energy. Now we're going to learn later that energy levels actually have, so the electron shell is divided into energy levels. The energy levels are also broken up into smaller categories, into sublevels. We call those orbitals, but we're going to talk about that later. Now, when we were talking about the electrons moving up to a higher energy level and back down again, we could have also used some different terminology. We could have said that the electron moves to an excited state and then falls back down to its ground state, emitting the energy as light. So that is what our excited and ground states are. Our excited state is a higher energy level reached by electrons that have gained energy. Right? So if an electron is in an excited state, that means it has moved up to a higher energy level or orbital by absorbing energy from an outside source. Now, the ground state is the energy level of an electron with the least amount of energy possible for that electron. So if an electron is at its ground state, that means that the atom has the lowest possible energy it can have. Now, when we are drawing atoms, we are always going, unless otherwise stated, are always going to be drawing them at the ground state. Okay? So we'll always see it at the ground state. This is because, right, that is the lowest energy state of the atom, and also what determines a lot of its bonding and its reactivity, right? Electrons, outermost electrons specifically, can move up and down, but this ground state is where what we think about when we think about how it interacts with other things. All right, so we're going to move on and talk about one last thing this class period, and that is we're going to learn how to draw a model of the atom. So we're going to learn how to draw the Bohr model. So everyone turn to page 2. Hopefully all of our definitions are done. Right here we see the Bohr model. Now this diagram should look familiar. We have seen this one before. We actually labeled it. So the Bohr model of the atom is like this. This is a picture of a Bohr model. We also call it the planetary model because in it we draw the nucleus like the sun and the electrons orbiting the nucleus like planets. So what are Bohr models? They are representations of the atom. And they are specifically representations of the atom that show the electrons orbiting the nucleus. Right? right, in concentric circles. So if you're like, what? That's what the word concentric, right? Concentric means, right, there's one circle and another and another and another. So it's a circle inside a circle inside a circle. Okay, so we're going to learn how to draw them right now. Now, heads up, you're going to need to write small because I didn't properly determine how much space we might need. So just heads up. So we're going to learn how to draw Bohr models. So there are only a few steps. But we got to make sure that we do each and every one. So number one, we need to draw. We need to figure out how many subatomic particles we need and draw the nucleus. So let's actually cross that out. Actually, we could have kept that. So determine number of protons, number of neutrons, and number of electrons. Now, we already know how to do this, but let's rewrite it so that we remember. Okay, so we can find the number of protons by looking at if you were thinking atomic number, well, congratulations, you are correct. Right? Our atomic number tells us the number of protons. We can find the number of neutrons. Now, we've talked about this before using the mass number. We haven't spent a lot of time talking about how to find it using the periodic table, but in fact, we can. If you look at the atomic weight on the periodic table and round it to the nearest whole number, that is basically the mass number of the atom, right? Granted, it's the mass number of probably the most common isotope, right? You can then subtract the number of protons, and that gives you the number of neutrons. So to find the number of neutrons, we are going to round your atomic weight to the nearest whole number. And then subtract the number of protons. Do not worry, we're going to do some of these together. It's all good. Okay, so then lastly, we need to determine number of electrons. So the number of electrons is easy because this is an atom, right? It is neutrally charged. So the number of electrons is equal to the number of protons. Step 2, right, is we're going to draw our nucleus. Step 3 is we're going to add our electrons in rings around the nucleus, following the rules. Now, there are some very important rules that we need to remember. There are 2 of them. Rule number 1, each energy level can only hold a specific number of electrons. Rule number 2, fill the inside towards the outside. Every inner level has to be full before you add one to a higher level. So we're going to write our rules over here. So rule 1. Each level can only hold a specific number of electrons. All right, that is very important. So quickly, we're going to go through how many each can hold. So level 1 holds 2 electrons. Okay? Level 2 right, would be like right here, holds 8 electrons, up to 8. Now, you don't have to completely fill them if you don't have enough to fill the level, but you got to fill it up entirely before you add another level. Now, this atom right here is carbon, so it only has 6 electrons, therefore only has 2 energy levels. But we're going to pretend and we're going to draw another level in here, right? We're going to say level number 3. Level number 3, it can hold 18 electrons, but is full with 8 electrons. So just to help us out here, I'm going to go through and I'm going to highlight this, right? Just so we can remember. Right? This is very important. And this is going to help us a lot. Now, you will get used to this. It will start to make sense. 2, 8, 18. And I will, later on, I'm going to tell you some sneaky ways to remember this. So that is rule number 1. Each level can only hold a specific number of electrons. So you will never see a Bohr model that has 3 electrons in level 2, or 9 electrons in level 8, or 30 electrons in level, sorry, there is no level 8. 9 electrons in level 2 or 30 in level 3. Right? You won't see that. You will only see them filled up to that level. Okay, so rule number 2. All inner levels must be full before adding a new level. This is very important, right? All inner levels have to be full before you add a new one. So that means you don't add electrons to level 3 and then 1 and then 2 and then 6, right? That does not happen. Okay? All right. So we are now going to practice drawing Bohr models, and it's going to be great. We are going to start off with, on page 9, we're going to do one together. Okay, we're going to do aluminum. And then you will finish the rest another time. So at this point, y'all, we are going to move on to look at page 9, and we are going to look at aluminum. Let's take a second, finish up your notes, and we are going to move on to aluminum. All right, so we're moving to page 9. So many pages. Page 9. Ooh, I opened right to it. What we see here, we have page 9. Remember, there's a little thing right here to remind us of what to do in case we forget. And we are not going to draw the easy ones. We are going to draw aluminum. Okay, so first we need to figure out how many particles we have. Okay, so aluminum is atomic number 13. That means that it has 13 protons, right? Atomic number 13, 13 protons. Now, to find its neutrons, we need to look at its average atomic mass, also known as its atomic weight. So its atomic weight is 26.96, I think. 26.96. So it's math 26.96. Now this number right here, we need to round to the nearest whole number. So the nearest whole number to 26.96 is, of course, 27, right? Sometimes you're going to need to round down depending on which number it is closer to. All right, to find the number of neutrons, we need to take 27, and this is the mass, and minus 13, which is the number of protons. This gives us 14 neutrons. Now, to find out the number of electrons, we just look at the protons, right? Number of protons is equal to the number of electrons in a neutral atom. And we have not yet learned about when they're not neutral. So right now we assume that they are both the same. So we have 13 electrons. Okay, so we've done step 1. It is now time to do step 2. We are going to draw our nucleus. So I'm going to put a sort of small circle in the center as to be our nucleus. Now I'm drawing it kind of small because we're going to have a number of layers of electrons. So try not to draw your nuclei too large. So in the middle, we are going to put our protons and our neutrons. So I'm going to write it exactly as I have it written here. 13p plus 14n to the 0. Now I am doing this rather than drawing a lot of circles because as you get to larger elements, those little circles, they're just really a lot. They get really complicated. So writing your nucleus like this is a lot simpler. Okay, so we have done our protons, we have done our neutrons. It is time to do our electrons. So first we are going to draw in our first energy level. So here we go. Now, our first energy level, if we remember from our notes, can hold up to 2 electrons. And all inner levels need to be full before we add to the next level. So we're going to add our first 2 electrons here. 1, 2. Now, we need a total of 13, so we are not done, not even close. So that means now that our first energy level is full, we can add a second. So our second level can hold up to 8 electrons. Now we've already used 2 of our 13. That means that we have 11 more. So that tells us our next energy level is also going to be full. So we're going to add 1, 2, 3, 4, 5, 6, 7, 8. Now we have 8 in the second, 2 in the first. We have used a total of 10 electrons. 2 plus 8 is 10. We are now going to add our final electrons. We have 3 left. We have 13 total, and we have already added 10 of them. Our last 3 are going to go in the third level. 1, 2, 3. And that is done. That is a completed and correct Bohr model of aluminum. Now, one thing I want to point out, you will notice I drew my electrons as lines. You don't have to do that. I find that easier to see, though, than drawing little dots. So you could also draw them as dots if you prefer. I prefer to draw them as lines because I can more clearly see which energy level they are in as they cross that line, right? And they're just easier for me to see than dots. You'll also notice that I drew my lines equally spaced around the energy level. That is a personal preference based on the fact that electrons are negatively charged and so therefore would repel each other as much as possible. And so that's why I draw them like that. If it's easier for you to keep track of by drawing them closer together, that is also 100% okay. And all right, we'll do a few more of these on the board together soon, and then you'll be working on the rest of your Bohr model of the atom worksheet. Great job.